Okay, now it's time to start this morning.
Okay. I hope I put the mic correctly. Okay. First of all, thanks for having me here, for the invitation to this workshop. And as Giuliano introduced, we'll try to give an overview about EFT formalism, but I want to start from, let's say, the experimental environment where we perform this measurement. So LHC at CERN is a Large Hadron Collider, and the goal of this machine is to uncover the universe, the structure of the universe, and to understand how it works. How is it done? It's done performing making particle collide. So we all know that the Large Hadron Collider is a huge collider of 27 kilometers, and inside protons circulate into opposite direction and collide in 4 points where there are 4 big experiments that are basically our eyes to explore this subnuclear interaction, to explore to achieve our goal of understanding better the structure of the universe. So I will give a small introduction about the experimental setup that we use to detect these events, so the collisions of protons. And I will take the example of the CMS experiment, which is the experiment where I work in. So CMS experiment is a small experiment because it's smaller than the others, than his brother Atlas, for example, but is actually very big because it's like 16 by 16 meters per 21 meters big detector, and is very heavy, 14,000 tons, because of all the materials that are necessary for the detectors. This is his version splitted in slices, and this happens when there are the upgrade activities going on during. But it's useful to see the internal structure of the experimental setup. So here is the beam pipe where protons circulate and collide in the center of this setup. You have to imagine when there are the collision, the setup is compact like this, but it's nice to see the inside. And all the rest is basically what allows us to see the outcome of these proton collisions. The outcome can be various things, particles of all kinds, basically. And we call them events. So when we have collisions of protons, the outcome is, we use this nomenclature, let's say. And we can have different events. So events where there are jets that develop in different angles, and these jets come from the hadronization of quarks of different kind, or we can have events with 4 clear leptons that we can really clearly reconstruct thanks to the characteristic of the detector. Or also we can have events like this with 2 high energy photons that we reconstruct in another kind of detector, which are these detectors that we use. There are different kinds, but basically the CMS experiment is a huge onion, if you want. Is built in concentric circles, let's say, that develop around the interaction point. And these layers are contain the different kind of detectors that allow us to see the different kind of particles. If this is the interaction point, around the interaction point, you have what we call the tracker that is made of silicon sensors that allow us to detect the trajectory of charged particles, so all leptons and charged hadrons that go through these layers, interact with the silicon and leave a little bit of charge, and then we can really reconstruct, matching the points, we can reconstruct the trajectory that this particle followed. Then right after we have the electromagnetic calorimeters, this green part that is there for reconstructing the energies of electrons and photons. And this is a destructive, let's say a destructive detector, because the particle is destroyed inside this detector in order to perform the measurement of its energy. Then just outside there is the hadronic calorimeter that basically has the same function as this one, but for hadrons, because hadrons behave differently from electrons and photons inside the detector, and we need a bigger structure to contain the shower development that is the outcome of the interaction of the hadronic particle with the material of the detector. Then outside of this, there is the superconducting solenoid that is basically the heart of the CMS experiment. Is the 4 Tesla magnet that allow us to bend the charge particle trajectories, and so to perform measurement of their momentum. And just outside there is the subdetector that gives the name to the CMS experiment, the muon system. In fact, CMS is called the compact muon collider. CMS, compact muon solenoid. Sorry. So the solenoid is very important, and also the muon are very important. They are very well reconstructed inside this experiment. Just a curiosity, these red part are called the return yoke of the magnet. They are a huge block of iron, and they are there in order to allow the magnetic field to go back and close the line fields in order to allow the particle, the muon particle trajectory to be bent also in the outside part, and so that we can reconstruct and measure the momentum of the muon particles so well in the muon detector. This was just to give an idea of the environment we work in, but of course we cannot use right after the data. I'm sorry. Okay.
Super, like the absolutely silly question. But if you go back to the slide,
yeah.
How are the programs being curved in the trajectory? Like, because in my head, one model I saw they are bent thanks to the magnet. But here, like, if I understand part of this, I consider the magnetic field is one step.
Yeah. Yes.
So, I mean,
the protons are not entering the CMS detector, basically. So the protons, no, wait. The protons are circulating in the beam pipe that is basically the axis around which the CMS detector is built. And they are bent using different kind of magnets all along the LHC. you have different kind of magnets because you need some magnets for bending the trajectories, some for collimating the trajectories, but these magnets for the protons are along the LHC. Then in the experiments, you don't want to see the protons. You are interested in the final state. Let's say this is, I mean, there are particular cases. Is solenoidal? Sorry? Yeah. Yes, exactly. So no, this gray part is a solenoid. So the magnetic field is basically going parallel to the beam, and then thanks to the return yoke of the magnet is closing these lines. So in the transverse plane, you can bend the particles, of course, inside the solenoid in one direction, and then on the other side. Okay. Okay. Of course, we need to decide which event we want to use for our analysis, because actually the rate of collisions is quite high inside the LHC. In principle, every 25 nanoseconds, you have a bunch of protons crossing and possible collisions. So a lot of mass. This is a pile-up distribution inside the Cms experiment. So a very important part of the analysis selection is the trigger. That means we need to decide which are the interesting events, the potentially interesting events that we want to study. And then after this, we store the data and we perform an offline selection that is based according to the type of analysis that we want to perform. Usually is not necessarily model independent. You want to target a specific signature, and so, for example, if you want to study Higgs boson decay into 4 leptons, you will ask for events that have 4 well-reconstructed leptons in the muon system chambers, or I mean, this depends on the signal that you want to study. Yes, and this is what I wanted to say for this slide. So just to be clear, we don't analyze the images of the collisions that we saw before. These really nice reconstructions of the development of the particle inside the detectors. Actually, what we use for the analysis is basically the kinematic information of the different particles. So we deal with tables like this in a way, where we have some kind of convention for enumerating the events that we record and we select, and then for each event we have information like the ID of the particle. The ID is given by taggers usually, but taking the information from the detectors in which this particle were reconstructed. For example, an electron, we know that is an electron because leave a trace in the tracker and in the electromagnetic calorimeters, and this way on for all the different particles. And then, of course, the momentum and the invariant mass of the reconstructed particles that we want to study in this particular event. We use this particular quantity that is called the transverse momentum PT. So basically is the projection of the momentum of the particle in the transverse plane. So the XY plane, where the Z is the line, is the axis parallel to the beam. This is done because ideally CMS is a it managed to reconstruct all the particles, but it is not really true because you miss neutrinos, for example, and also in the z-axis you can have some holes in the experimental setup because of, for example, the beam pipe that has to pass. So it's structural hole, and so you are not really hermetic. But in the transverse plane, yes. So you can really have a lot of information about these particles. And yeah, just to complete, to say something about the data format that we have is something like this. Usually we, historically, root has been developed for managing this kind of data formats, but recently with the coming of Python, also pandas data frame are largely being used. And a final remark is that both data, so recorded data, and the Monte Carlo simulations are have the same structure, apart from some weights that we have only, for example, in the Monte Carlo, in the simulated event for normalization purposes and corrections and this kind of stuff. So, yep, sure.
Thanks.
Not really. I mean, it depends usually on the kind of analysis that you do. Root is nice because it's C-based, so it's very fast and also useful to deal with large data sets. But of course, data frames, pandas are easy to use. The drawback could be that if you have a very big data set, it needs very long time to be loaded, for example, but nothing that cannot be overcome.
Okay, thanks.
Usually what is done is like a mixture of the two things. Yeah, exactly. And so basically, this is a plot that we can obtain after the selection of events in the X2 for lepton final state. The black points represent the recorded data, while the colored one part is Monte Carlo simulation. For example, this quantity that we are looking at is the invariant mass of the four-lepton system, and this red part is the nice Higgs boson peak, and we see and we are happy that all the data are following very nicely the expected distribution of the Monte Carlo. This simulation is one of the very important tools that we have in particle physics, because it's basically the expected knowledge that we have of the model. And this is obtained from, let's say, first principle, from the knowledge that we have of the standard model of particle physics. We already heard about this model in these days, so I will try to be quick, but basically this is the best understanding that we have right now of particle physics interactions. And you have, basically is the theory that we use to compare the data with in order to understand if there are deviations, if there is new physics. And let's say it's a theory that is growing in time. So if, for example, before its discovery, the Higgs boson was kind of not included in the standard model. When the experimental, I mean, it was expected, but it was not verified. When the experiments discovered that the particle is really actually there, then let's say this missing piece was completed. And now we're trying to understand if there is something more. But yeah, just quickly, basically, we have matter particles that are divided in quarks and leptons, and the normal matter that we have is, these particles are divided in 3 generations, and the usual normal particle like protons and neutrons are obtained from the first generation fermions. And then we have force carrier particles that are the vector bosons and the photons and gluons that are the force carriers, so the particle responsible of the fundamental interaction, basically. And then the famous Higgs boson that is responsible for the elementary particle mass, basically. The model is a gauge theory, and thanks to these symmetries, we can fit the Lagrangian of the model on a mug. And here you have the different parts. So gauge boson, then the fermion kinematics, then the Yukawa interaction that are basically what allows the fermions to gain mass, and then the scalar potential with the information about the Higgs boson, and also, for example, its self-couplings and main interesting stuff. So just a quick parenthesis on something that might be useful for the next part of the talk. So the statistical analysis that we perform, basically, we have this model, and what we do is test the data that we collect at the experiments against this model. And the way it's done is performing a statistical analysis. For each analysis, we define a likelihood function as the Parton distribution, probability density function. This is wrong. I have to fix it. Sorry. The probability density function that characterizes a set of experimental observable that is considered in the analysis given the parameters of the model. Usually for LHC searches, especially for Higgs searches and measurements, what is done is that we define a signal strength modifier that multiplies the expected cross-section of the standard model, just to have a simple parameter that stays between 0 and 1, and then we can use this as a parameter of interest of our fit. And then we include the systematic uncertainties as nuisance parameters, and of course, every nuisance parameter has its own probability density function. And then we build the likelihood based on observed data or simulated data, according to what we want to obtain, if the actual measurement or the expected measurement. And the likelihood will have this form, and this C could be, for example, the channels that we consider in the analysis. If we divide the events into categories, we will have an independent likelihood per each category that will enter the total likelihood. And from this, we can then do hypothesis testing, usually likelihood ratio test, in evaluating the likelihood according to different alternative hypotheses. This, for example, is one of the measurements that was done in run 1 to understand if the Higgs boson was a scalar or a pseudo-scalar, so measuring is spin parity. And but this kind of test statistics can be used for many different measurement, like quantifying an excess. So if we want to understand if there is a new particle, for example, in a certain mass distribution, or setting upper limits if we don't see anything, or then measuring parameters of the model. So we said that standard model is the theory, but of course it's not yet the theory of everything, because we know that some things are missing, like gravity, like matter-antimatter symmetries is not explained. So we search for new physics trying to achieve this final theory that explains everything. Maybe one day we will be there. But basically, how can we study this new physics? We can search for deviations from the standard model that, again, represents our state-of-the-art knowledge. And this can be done with an effective field theory. What is an effective field theory? It's basically an approximation. It's an approximated theory that includes all the degrees of freedom of a certain physical phenomena, but ignores the substructure that are important at higher energies. Of course, since it's effective, it's valid up to a certain regime. For example, if we have new physics that is beyond the reach of the colliders, we could have these effects of deviations, especially in the tails of the distribution, due to this new physics. But the only way that we can access this is to measure this deviation and infer something on the higher energy theory. So we said that it parameterizes the effect of this new physics. This new physics is at a scale lambda that is very high, while we are in a regime of energy E that is much lower than lambda. And so we can expand our Lagrangian of the model in terms of Taylor expansion in terms of E over lambda. Basically, we add to the standard model Lagrangian a series expansion in terms of these energy hypothesis, and this expansion contain operators that can describe point-like interactions between different particles, and each operator is weighted by free parameter that is a Wilson coefficient that can describe the new physics effect. A brief example: the Fermi's interaction for describing beta decays. It was introduced for explaining how this kind of decays, weak decay work. And it works really well at the energy, at low energy, let's say. So it's a point-like interaction where we say the neutron interacts with the proton and then emits an electron and a neutrino. But the thing is, this theory, the cross-section of this process was then growing as the square of the energy, and of course then it cannot be valid at higher energies. And in fact, this was found to be the effective field theory for a higher energy theory, that is the electroweak interaction, basically, where we have, instead of a point-like interaction, we have two interactions mediated by the vector bosons. And in this case, the scale is more or less the mass of the boson that enters this interaction. And so in a sense is what we're trying to do with effective field theory is something similar. So we have the measurement that is valid at a energy regime E, and we know that model and fields and the standard model with its fields and symmetries is valid at these energies. And then we expand using in terms of this higher energy scale, and we describe the new physics effect in terms of this Wilson coefficient. What is nice is that we can then infer something about the higher energy theory, measuring these free parameters of the theory, and then hopefully one day arrive to have the description of the high energy theory. In our, going back to our case, so the standard model effective field theory again is we make this assumption. So we say new physics is decoupled from the physics that we have at, let's say, today's energy scales, and but we assume that the standard model symmetries and fields are still valid at this energy, and then we expanded the Lagrangian in terms of operators and Wilson coefficients. What are these terms? Something that I forgot to mention the Lagrangian of the standard model is dimension 4, while the operators that we consider in the Taylor expansion are higher orders. So we have the order 5 that contains information about neutrino masses, then order 6 that likely contain dominant effect for new physics contribution, then a lepton number violating term, then some other terms that can be interesting for some particular processes at the LHC where there are multiple gauge and Higgs boson involved. But since, of course, we have this term, the denominator, the higher we go in dimension, the lower is the effect of these terms. So this is all the not all is some of the operators is a basis of operators that we can have at dimension 6 for the expansion of the EFT standard model Lagrangian. These are 59 operators, but for example, some are not included, like CP violating. So I mean, if we consider everything is like 200 operators in total, people can correct me if the number is not correct. But then, of course, if we go to higher dimensions and we consider like also dimension 8, the number of these things increases. So it's not a simple problem, and there are a lot of techniques that are used, and Robert will talk about more in detail about how to deal with these many dimensions, basically. So concluding, we can use effective field theory to describe beyond standard model effects, and it's a nice way to do it because we don't have to do many assumptions on the higher energy theory. So we can be in a way model independent in the search of new physics, and then this approach systematically includes all the BSM effects, since we are considering all the possible deviations embedded in these operators. And in a way, is a universal language that can be used between different, I mean, even if different experimental setups are used, this language can allow us to compare and combine measurement. And the combination of measurement is really important because measurement of Higgs related variables and top and electroweak can have sensitivities to different directions of in the effective field theory. And so taking information from the different areas is really important to have a more complete description of these effective field theory parameters, and so to infer more precisely something about the higher energy theory that one day maybe we will reach. Thank you.
Okay, I'll continue on machine learning for SMEFT. I'll try to summarize certain aspects of the previous talk to give you an idea of what we are doing in experiment. I need to talk a little bit about modeling in the context of SMEFT analysis, and let's go very briefly through what we are doing in experiment. We have a very high degree in this field of model predictivity. The standard model Lagrangian fits on a coffee mug. We collide protons with an initial state that's described by the parton distribution functions inside the proton, consisting of an enormous amount of measurements that are put together in a model of the proton, where the QCD splitting functions analytically enter, which are 10, 12 pages of analytic calculations describing a model of the proton that we then fit and we make predictions, and that's just the initial state. The initial state then produce yeah, the initial state then produce virtual particles in the quantum sense. These are the ones that we are mostly interested in. These have the interesting effects. And then these particles decay. All that is described by quantum field theories, but things don't stop here. The strongly interacting particles shower, hadronize, and then the hadrons decay. All that is described again by a mixture of analytic model predictions, measurements, and in the case of shower, empirically motivated or physics-inspired models that give important aspects of the final state properties, but which are, for example, very hard to perturbatively improve in the sense of a perturbation theory. Now we arrive at the final state, or what in theory, the theorists call the final state, but things don't stop here. We have metastable particles that we've seen now traverse the detector, get bent in the magnetic field, and at some point hit the detector material. And the modeling of these effects is again partially analytically known as ionization, scintillation, Bremsstrahlung effects, and so on. In principle, one could compute all these things, but the detectors are too complicated. And these interactions, if you look at like what's known about beta Bloch, just giving you the ionization tool, is these are enormously complicated models that, in fact, we parameterize in some way, put them in the shear 4, and run the detector simulation. The signals then get shaped by the electronics. This, in fact, is the moment when data and simulation begin to move in parallel, because the real data enters at this stage. Then we have digitized signals, and we perform local reconstruction in the detector. We look at the individual detector cells, start working with the things there, reduce the backgrounds, do particle flow, topological clusters, whatever method is preferred, and eventually we reconstruct final state objects, and then we make distributions, and at that stage we compare with some parametrized theory predictions from standard model effective theory or any other model, and then we try to draw conclusions. So what's the best way to do that? Turn on the detector, you collect a bunch of events. So that's a family of events, and in frequentist statistics, in a sense of frequentist statistics, we look at the likelihood. We look at the likelihood functions. That data is described by a vector, by a set of feature vectors. That's the data set, and we have our theory parameters. That could be standard model effective field theory, Wilson coefficients, or anything else. The likelihood factorizes into a simple number of how many events there are. There's nothing for a machine to learn about the total number of events, so usually this is just a factor that's not very interesting, and then a factor of what the events look like. And the maximum likelihood estimate, because of its statistically nice properties, it can then be used to find the maximum likelihood of the data under a given model hypothesis. Yeah. Say again? Oh, I said it doesn't matter for the machine learning. It doesn't matter because we're going to talk about machine learning and going to talk about how to separate a signal hypothesis from a standard model hypothesis. Then the total number of events is not something that the machine needs to learn. The training, for example, happens after, as Alessandra has explained, after some trigger selection, some cleaning cuts, then you get a total number of events. But if you turn on LHC, for example, let it run, and these things happened, okay? Turned on in 2009, look at the data quality monitoring plot, you get an expectation. You immediately saw from the scale of the data that we were taking, which was within 10% of with all the early stage calibration that we had, that the standard model survives this test just by looking at the total number of collected events. I'm saying that the total number does have information. It is here, this cross section, the total cross section depends on the model parameters. It has information. It's a difference whether you see 100 events when you expect 10 or whether you see 10 when you expect 10. That information it has, but there's nothing for a machine to learn from a number. The moment we, yeah, so we know it already. We've already learned it. The moment we learned counting, and
okay, thank you.
Good. So, in the sense of hypothesis tests, there's the Newman-Pearson lemma that appeared yesterday. It tells us that if we want to do hypothesis tests, the optimal test statistics is the ratio of two likelihoods. Here at the left-hand side, I haven't even specified whether the data set I factor in the structure that it's individual events, or this could also be ensemble methods here. On the right-hand side, the logarithm of the individual distribution of the distribution of individual events appears under the sum. The way to understand the Newman-Pearson lemma is it tells us that the log likelihood ratio provides us, if you do a hypothesis test under two hypothesis background or the standard model or a signal hypothesis, it provides us with a test statistic that has for a given signal efficiency, it has the lowest mis-ID probability. So this quantity you should compute. It is, of course, if you look at millions of events like that, all of which have tens of thousands of degrees of freedom, these likelihood functions are prohibitively complicated. So in traditional analysis, we make drastic ad hoc simplifications. We count some objects, we then take our model, identify some sensitive observables, can be an invariant mass or a transverse momentum. We aggregate the data in bins, we group the things. Then we usually define a Poisson likelihood because data in bins is Poissonian distributed. And then we obtain a binned maximum likelihood estimate, and we end up here. We use the likelihood ratios to obtain confidence limits based on frequentist hypothesis tests. That is the result, and then we make a propaganda plots like these. One can call these propaganda plots because it's not a great deal of hard facts in there. What is, however, in there is a very a summary of something very deep that we uncovered about the Higgs sector that was predicted in the standard model, namely that the mass and the coupling strength really are proportional, and that is exhibited by this plot. So it's something very deep that we find, and now we want to go further. We've done this with many fundamental models like supersymmetry, huge families of exotica models, all predicting different types of short distance physics, all of which so far we have ruled out. We've removed parameter space, and now we essentially say, okay, let's assume there are no new degrees of freedom. Let's assume the standard model symmetries are right, but let us not assume that nothing can be there at the high scale. So with the first two conditions, whatever can you get? You can get a family of operators organized in the mass dimensions. There are 59 degrees of freedom at mass dimension 6, and these are the things that we search. If you believe in the standard model, then what that means is you say that the standard model is valued to all energy scales, which means it must be renormalizable, which means it can only work with operators up to dimension 4, and then all these SMEF effects are excluded. Here we allow symmetry preserving all the symmetry preserving operators without new degrees of freedom, but in turn it means these interactions are non-renormalizable. They go to mass dimension 6. If you take it too far, you create infinities, and therefore validity is an important aspect that I will not discuss. In turn, I will explain example machine learning uses in recent SMEF analysis. I hope I can explain. It's 12, right? This means 12. We have until 1. Okay. Well, you need to say very explicitly what you're doing. You have a dimension 6 operator, and it's in the same sense non-renormalizable as if you put in Fermi theory. You have a 4 fermion operator mass dimension 6. Produces and you do not have enough degrees of freedom to, at all loop levels, absorb all divergences. You need to in this sense. It's valid below a scale lambda. That's what I'm saying. That's all I'm saying. Okay. I'm just. I don't think this is a controversial statement. It's true for all effective theories. Okay, we can be done by 1. So. Let's now go through a few SMEF analysis that we do in experiment, like in real world. I try to give you an idea of where we are in the experiment. Then the challenge that lies ahead, which is a big one, and then a few newer ideas on how to tackle the challenge. I start in the same way as we started with yesterday, namely with the likelihood ratio trick. We try to discern 2 hypotheses using data. We write down a loss function for a discriminator that depends on a model. X is the observables. C is a binary 0 or 1, which could be signal or background, and then we regress in some truth label. One can execute this sum, and if you functionally differentiate with respect to the loss, so take a function with maximum express that maximally can express everything, you find that in this limit you actually recover the ratio of the likelihoods with 1 over 1 plus r. That's the likelihood ratio trick, and it's something at the very heart of all hypotheses of all the sensitivity studies, because that is the thing the Newman-Pearson lemma tells you to learn. If you can learn that, you will have optimality in a well-defined sense. Let's now look at the challenge. And I start with a few examples from the Higgs sector. So the Higgs sector, for those who are not in high energy physics, the Higgs boson can be produced by a variety of channels. There are 6 or 7 that we can discern. Here's 4 of them: gluon-gluon fusion, vector boson fusion, associate production with a boson, and with 2 top quarks. The numbers here, the production cross-section, giving you an idea about the relative probability. So here is the most, the strong, the highest, the strongest production channel. The dots here indicate different standard model effective theory operators. So here we can, for example, check the top Higgs Yukawa coupling in a production mechanism like this. And here we have the Higgs to boson amplitudes. The Higgs sector is very special because of its threefold complexities. You not only have production mechanisms, but also different many different decay channels. I list here the branching ratios that tell you that most of the time your Higgs will go to 2 peak quarks. Sometimes it will go to C bosons, which you can then see very clearly. There are also SMEF defects in the Higgs decays. So what you always get with the Higgs boson couplings with loop-induced, very important Higgs to diphoton decays, and we have the fermion couplings. What you always get is a mixture of the two, and that makes Higgs analysis involved and connected. We start with Higgs to ZZ into 4 leptons. This is the first example. So we combine here the highest production, the highest cross-section production channel with one of the cleanest decays. That's what we call the golden channel. It combines favorable properties. However, it has some low branching ratio. The Higgs to CC is only 2.6%. The C decays leptonically in only with a low branching ratio into leptons, and that reduces the statistical power. With a bunch of SMEF, standard model effective field theory, SMEF operators here, this analysis looks at the 10 different operators that are listed here. These are mostly the bosonic ones, so where the Higgs couples to the C boson. The strategy of the analysis is the following. It defines a bunch of reconstructed event categories. These are listed here, and then it groups different production modes. So the idea of the analysis was, let's look at the Higgs to CC bar because that's clean. Let's try to measure all the different production modes that go into there, and then we interpret this in standard model effective theory. So you can see that here there's the categories. These are reconstructed, and these are the generated ones. These are coming from the model, the different production modes, and you see there is a wild mixture in these compositions. So what's done is MLPs are trained on a bunch of observables. In this case, it's only 2 to 7 variables. This is comparably few. Typical analyses are in the 20, 30, 40 observables. What's different here is that recurrent neural networks are used on variable length inputs from the leptons, electrons or muons, and the jets. And those are trained together with dense layers that are put put together with this in this topology, and then multi-classification of the different production modes, gluon-gluon fusion, vector boson fusion, and a background category is attempted. There's an implicit message here, namely, I did not put any detail on what this network looks like because it's not in the paper. I do not even know whether these are LSTMs. I think they are. Are they? Yes. Multi-layer perceptron neural network. Just a neural network. This Chargot, maybe. Please keep asking me these Chargot questions. I did not translate everything. It's just a dense layer. Nothing very interesting. But we will. This analysis will be is very difficult to reproduce in any sense. If you're outside, you do not even know what the type of network is, and that will play into the challenge that we have in the future. Nonetheless, for almost each bin, a discriminator is trained that separates the production categories, and then cross sections are measured. Okay. Now we come back to what Alessandra has said. In a practical application, things look a bit complicated because if you put in some detail, they actually are, but the structure is quite simple. We have the measurements, a binned version of the discriminator. So here's a gluon-gluon fusion discriminator value. Here's a VBF one. It gives us data in black dots. It gives us in blue here the production modes, and in red is the background. With these, we feel a Poisson likelihood that's parametrized with the signal strength sigma, and this P stands for one of these production modes. And then we find a way to deal with nuisances. This is a profiled likelihood test statistic. Not going to go into the detail there, but I need to mention that we handle the system. One second. We handle the systematic uncertainties, and then we fit and obtain values that's listed here for the production cross sections. Yeah. These neural networks, so this configuration that is listed here in each of the reconstruction bins, I was going to explain it, so it's a good moment to explain it now, gives you, it learns to separate the production, the processes that are listed here. So it learns the likelihood ratio at the event level that will optimally separate these processes. That's what it does. So it has nothing to do with SMEFT. We are on slide 10. I haven't done anything on machine learning in SMEFT. These MLPs learn to separate different production modes of signal and the background simultaneously using the likelihood ratio trick. There are, wait, slowly. There are, for each bin, we have such a structure. So you take these variables listed here, put them in here. You take the lepton RNN, put it in here. In this case, you do not have the jets. You get multi-classification for the first bin, and then you repeat. You get 9 or whatever it is. Yes. Well, these are generated ones, but the neural network arrangement tries to approximate these. That's right. That's right. Wait, yeah, I need to say optimality for what? Here is optimality. Here we use the likelihood ratio for. Let me finish the next slide because I think I will answer exactly the question. So here we are, and we have learned the different production cross sections using the likelihood trick. So in a frequentist setting, we should be with some caveats optimal with respect to the measurements of the cross sections, but the cross sections are not the EFT parameters. What do we do for the EFT parameters? In this analysis, the signal strength, the cross section is multiplied with a signal strength, and the signal strength is now modified according to a theory prediction consisting of production type modifications, of decay type modifications, these things are separated, and of acceptance type modifications, because this 4-lepton decay very sensibly depends on some of the operators, and your detector acceptance does not commute with that, and these effects are even huge. We go down to 20% acceptance as a function of the Wilson coefficient that's listed here as CHP. So this is a let me finish this. So this is a very large effect. So we have products of parameter-dependent factors that we then put into the signal strength modifiers, which modify the signal strength. Our likelihood becomes a function of the parameter, and we perform the exact same statistical procedure to arrive at confidence limits now on the SMEFT parameters. And you see here very complex contours, which are indeed an effect of the interplay of these many theta-dependent factors. For example, here in this region, you compensate, and you have a compensation of a SMEFT effect in the acceptance and in the production. Production tells you to increase, acceptance says, yeah, you increase, but you see less. Things cancel, you cannot tell it apart from the standard model. Okay, maybe now is a good moment, because that's a traditional way of doing things. Yeah. We did not assure this. That's the point. This is machine learning for SMEF measurements. It is in fact a learning of the likelihood ratio of production modes. That's what it always was. It's just a reinterpretation of a production mode. We call this STXS. A lot of jargon and technical details. But you see, you make a standard model measurement and then you reinterpret it. That's what you do. There's no machine, we're on slide 13, and we have not done machine learning of SMEF defects whatsoever. We did a learning of production modes to increase the sensitivity for a reinterpretation, but that could go wrong. So let's do the next analysis, which is TTH multi-lepton, which addresses this point. But it's good people are following. These are in the acceptance. These are factored in the acceptance. So in the decay and the acceptance. Partial, yeah. This. Yeah, that's right. On the other hand, on the other hand, the question is absolutely valid, and it's a point that has to be addressed, even if it's small for this particle. It's different for the top quark, for example. Hadronic top quark decays, you got to be much more careful. But these things are, of course, these are the things. If you break your noble strategy down into reality, these are the things one has to worry about. So let's now look at machine learning of SMEF, which is equally simple, conceptually at least. In this analysis, which is from CMS, we focus on the TTH production mode. We stay there. However, we look at the different decay modes. There are, for example, for tagging this tau-tau decay mode, which is not the focus of the talk. There are deep convolutional neural networks identifying these taus, which are really sophisticated, finely tuned, complex machine learning applications. It just has nothing to do with SMEF, and therefore I do not discuss it. It uses drag and calorimetry and all the information that you can get about the decay, that you can learn about the taus. There are also, in the sense of the previous analysis, 3 deep neural networks for signal and background separation. So there's lots of machine learning going in there that is not SMEF specific, just to remove the background. Now we are in a TTH signal selection after some MVA cuts, and the analysis targets the Yukawa coupling, so the red dot here. And the Yukawa coupling can, the SMEF modification of the Yukawa coupling here is an operator that is not real, so its coefficient in the Lagrangian can be a complex number, and the complex phase is related to CP violation. CP violation is that standard model symmetry that's intimately related to the meta antimatter asymmetry. Is very interesting. It's also interesting because on theory grounds it should be restricted in the bosonic sector. So it's a good way of looking at things. What the analysis does is it trains, it uses machine learning, in this case a gradient boosted decision tree, XGBoost, on 38 input features, and it learns the difference between the CP even signal and the CP odd signal. So you take your signal simulation, take the standard model CP even, make it CP odd. In the simulation, things change according to the diagram shown here. So red versus blue, and you got 37 more of such distributions, put it into a BDT, boosted decision tree. Doesn't matter what it is. It's supposed to learn the likelihood ratio, and that's exactly what it does. And then you get a discriminator shape that you can fit to the data. I picked here one of the channels. This is the 3 lepton category. And again, the black dots are the data. The TTH is CP even and CP odd, as are some suppressed production modes. And things are fit here to the data. So here we have learned, using the likelihood ratio trick, the cross-section ratio between two different hypotheses. We make a signal selection, and instead of fitting just a standard model, we fit these 2 components, and we extract these exclusion contours in the, here's the CP violating one, that's the CP preserving one. So that's like the simplest example of learning of the SMEFT effects with a machine that you can get. Okay.
From previous, there are other words that try to learn the difference between CP even and CP odd coupling in TTH, and they always found, using some set of observables, that they couldn't get it to be statistically distinguishable event by event, but simply in a global manner, looking at the what kind of variables are you using here to differentiate between the CP even and CP odd? Are you using these CP odd combinations of all the momenta?
Here, for example, one of the discriminating ones is the invariant mass of the full reconstructed TTH system. That's essentially just the scale of the whole event. If you look at the paper, they really cover everything that you can reasonably cover without going to the individual particle level. So there is all the kinematic properties of all the many. Each top decays to a W. W gives you 2 jets, or these are leptonics, so it gives you a lepton and a neutrino. You have the Higgs decays in various ways. You have 5, 6 leptons. You have many jets. You have taus. You have missing energy. You have tons of channels, tons of variables in each channel that you train with. I'm trying to elucidate the principle here. There's more than one. I mean, for each of the decay modes, there's an.
But it's in the correlations, because there it doesn't seem to be able to distinguish between the.
This is just the input.
No, yeah, but if you look at the I mean.
No, it cannot, because things are hard.
Yeah.
Things are hard.
Yeah, that's why the question was, because it's a very hard
Look
problem.
here, yeah. I mean, this is CP. You are right. I didn't show you the output distribution, how separated it is. But you can see that. I mean, that's your data. Look at red versus pink. Can you increase the pink a little bit without getting in conflict? Yes, you can. That's saying that this axis here is not very well constrained. Okay, this is in the language of the kappa framework, which you have to translate to EFT, but in this case it's 1-to-1. The point is that we learned, that we tried to here we try to learn the EFT effects.
Thank you.
Good. So the problem with this analysis is not its, yeah, sure. This is all binned. This is binned. Yeah, this is binned. And unless I'm completely lost, this is a binned analysis.
So yet
I did not even check. But,
yeah.
Yeah.
Just for summarize, maybe
we will go to unbinned towards. I will talk about unbinned analysis.
So at this stage, a lot of machine learning is used, but mostly for cutting, right? And for
binning. I mean,
exactly.
If you make 1 million bins here, it becomes unbinned. You can take a limit.
This is the only example in which something like a discriminator between EFT, or let's say CP odd version of EFT and CP even, has been used, rather than all the techniques deployed for the standard model and then just translated blindly, if you want to.
That's right. That's
okay.
right.
Good.
That's right. There's one more. We take You see, from a conceptual point of view, these things are simple. This is not very advanced usage of machine learning here, okay? We're trying our best. The issue here is there's a dominant top background here, TT plus a C boson. Now, the standard model effective field theory effects really contribute everywhere. So you're extracting the CP structure on sitting on a mountain of background that could move because other operators could be off. So what this analysis tells you is that you should look at top quark physics first, because top quarks can be reconstructed more purely. And indeed, it's different people who do that. I did many analyses in the top sector, not the latest one here. Here, now we move to the third analysis, which also uses the likelihood ratio trick. Now using going a bit deeper, we studied a top quark C boson coupling. As we've seen, this is important for SMEFT, for Higgs analysis and many other things. This analysis exploits the kinematic differences in the top quark final state. So you have TT bar with single top, we have WT, S channel, and then we have TTC, which we can isolate very well, and TCQ, which sits together with TTC. This analysis uses deep neural nets. It's again, it uses it for classifying background and signal, which is not SMEFT specific, so it does that. It uses 33 mostly kinematical properties. There are 8 neural networks. This is just, I think they are 2-layered, but there are many more nodes than what is shown here. So this analysis does a standard model background separation using neural nets, but it also learns the EFT effects. It exploits, in some sense, it tries to exploit the likelihood ratio trick all the way. Separately for each limit setting attempt. So you want to set a one-dimensional limit on a specific Wilson coefficient. There's a neural network trained that learns the differences in the kinematical spectra of signal versus background. So it learns the likelihood ratio between different SMEFT hypotheses. Here are the limit contours. Maybe I should not discuss the operators, although I'm interested in these. These are the weak dipole interactions of the top quark. There are 2 coefficients here, and these are the modifications of the top quarks vector couplings. There are also 2 coefficients here. In total, there are 5 operators, so you have a 5-dimensional measurement space. The analysis does 1-dimensional, 2-dimensional, and even a 5-dimensional limit. And in each case, now I tell you what they do, which is a little bit of a shortcoming. In each case, let's look at the 2-dimensional limit. They perform a training of the standard model hypothesis simulated here at the center versus a signal that's sampled from the whole parameter space. There's a coarse grid of signal points selected here. Each one will have different kinematic features, and you would think that the neural network can then try to separate or should be able to try to separate all of them. Now, this analysis currently has the best limits on these operators. But if you think about what is happening here, there is a sum over training points. I call this theta. That's the parameter point is summed over the training points that were decided to be chosen. What happens here is that you actually learn the average of the signal simulation. Now, that's fine. If you do not know that the signal simulation actually has a polynomial structure, and that polynomial can have linear terms and quadratic terms. In this analysis, the quadratic terms dominate, and that's why it is fine, because you average over signals with positive values and with negative values, and the effects on the cross sections, because the quadratic terms dominate, have the same sign, the minus sign cancels. But this is not a strategy that scales, because if we enter a regime, and here we actually close, where the linear term dominates, then you will, in your simulation, get cancellations that the machine will see of the linear term in the predicted distribution, okay? So it is not necessarily wise to train on a mixture of signal. It's not necessarily wise to send mixed signals to the loss functions, because it may just be averaged out and you will learn nothing or the wrong things. So here is, but before, now we can discuss the part about the state of the art ends. The next things are the challenge and what we should be doing differently.
I was just saying
It's a
that,
good
like,
moment
so
for
in this
questions.
case, you are really trying to use the full glory, let's say, likelihood trick to compute R, to compute the likelihood ratio, EFT over standard model.
That's right.
In this analysis, they're trying to do that.
Yeah.
But you're saying that they're not actually they're not actually computing that. They're computing so a non-optimal ratio, which is the average of these training points over.
Correct.
Okay, I understand.
Correct. And it doesn't matter as long as the quadratic dominate. Well, yeah, but yes, we have a better way of doing things. Let's discuss it. Okay, good.
So maybe this is the better way that you're talking about. Why, if you go to the next slide, I think I made an assumption that I guess is not true. I thought your f hat function was also a function of theta.
Say this again.
But apparently not. Okay.
Is this going to come? I'm trying to make a narrative here. That's what should happen. You say that the loss function is a function, should be a function of theta. It should be correct.
But
Can you, maybe I did not, can you just repeat? I did not, wasn't all.
yeah, no, that's exactly what I said. But then if it's not a function of theta, if you go to the previous slide, how did you make those contours? Because with just that R function, if it's not a function of theta, how do you make that red contour?
This is just a training. This is just the training of. This is the training of the class. This is the training of the classifier. You still get a prediction. The classifier learns the average of the signals. You predict it on. You get a distribution, and it will not be a perfectly learned likelihood ratio. It will be a suboptimal test statistic, but it is still a test statistic. It still has sensitivity to something that's not well defined in a hypothesis sense, because you trained on a mixture, and from that you define a binned Poissonian likelihood, and that gives you your frequentist confidence.
Okay, good. So I mean, in some sense, this is a good thing, because then I was going to ask a different question. So this is a good thing in that you have a classifier. It's somehow a good average classifier over the space of EFTs, but you don't actually use the classifier, despite the fact that there's this likelihood ratio interpretation. You don't actually use that classifier to determine the contours, even though you could if you had learned the correct function.
You're right. Yeah. I think you, as far as I can comprehend this, I think you're right. So
so this is more about the CP tagger, but maybe it applies for this one as well. But how would you validate such a tagger, or like measure scale factors for its performance, like for CP?
This is a difficult and analysis dependent question. Usually
for that specific one, maybe then.
Which one?
The TPH, like the tagger for CP even versus CP odd.
Usually, so I cannot tell you whether they work. Usually, what I mean, the normal strategy is you go through your list of systematic uncertainties and you make hypotheses carefully of what the uncovered systematic effect could be. After all, it's just a complicated a function of your input. So most of the systematics are experimental and theoretical, and you need to make sure that you do not that you do not learn something from details of the simulation that you do not have control over. And then the validation is typically performed in control regions, and then it becomes a matter of then you check the performance in the control regions, and typically if things agree within uncertainties, you do not put extra systematics because of the training. What I'm trying to say is that you have to be very specific about what kind of systematic you ask me here. What is it that is uncovered? And then I can answer.
So just the tagger mismodeling. So is there like a control region?
That's a mismodeling of the data. If you that's a mismodeling. That's a mismodeling of the data that's covered by the systematics of the inputs. So you could be worried about the modeling of the correlations, because you should not be worried about the jet energy correction uncertainties, provided you believe that we assess correctly that we correctly assess these. Same goes for leptons. Now we have 38 observables, and you could be worried that the correlation, the modeling of the uncertainty correlation is inappropriate, giving you fake sensitivity that you don't have. In this case, you typically vary the inputs according to an ad hoc hypothesis that you make about those correlations. So you say, what if the jet energy correction measurement of the flavor hadron, the flavor composition that enters the jet energy correction has a large effect on, or is correlated with what we learn on the leptons. So in that case, what you typically do is you modify your simulation. You go to an azimuth fit. You modify the make a reasonable guess of the worst case scenario, what this correlation could be if things go very wrong. You inject everything and you see how much the output varies, and then you assess, and then you add a small or appropriate extra uncertainty. That's why these papers are long, and that's exactly where the discussions then always end up for systematically limited analysis. How do you do things? How do you a typical problem is heavy flavor production in complex final states. TT plus a C boson plus BB plus 2 Bs. It's extremely hard, and you need to do many of such checks. Okay, I think I should finish now. I should maybe before we talk about what we should be doing next, look at the complexity of the problem. I already explained to you, or shown to you, how difficult life is in the Higgs sector with production channels and decay channels. And then this Higgs sector gets large backgrounds from all other sectors, in particular top quarks. And moreover, the top quarks appear inside loops, producing the Higgs boson and in the Higgs boson decays. So everything is intertwined. And here I list the most, in the left two columns, I list the most important top final state that we will have to put in, starting with TT bar, going all the way to 4 top with very different production cross sections, very different systematics. And those tackle mostly, of course, the fermion boson couplings, but we also have couplings amongst the bosons, which we can test in electroweak production of dibosons. And there's an enormous number of possibilities there. And the diboson vector boson fusion analysis all receive very large background contributions from the diagrams where you don't have these 2 extra jets. So we have a very wild mixture that we need to get under control. In my opinion, that's an opinion that one can have. We have to solve this challenge of a global interpretation of 59 operators in hundreds of distributions with thousands of bins and thousands of uncertainties by going by arranging it in a triangular matrix. One need to start, I think, with high multidimensional analysis on the standard model candles, because that's what we always do. When we turn on the LHC, we were searching for supersymmetry in the sense that we were assessing there is a top quark, there is a W boson. We compare this. There is Trillian, there is a C boson was the first thing we saw, and after seeing that, you get some idea about the backgrounds, and then you can do a search. And here we need to do the same thing. We need a high-dimensional SMEFT analysis on the boring standard model candles, Trillian, TT bar, and WZ. See, these are completely pure. You have no background correlations, and these are the things that we need to have. Then we can go to TTC, TTW, and the top final states. These are the signal regions here that they have like 10% background, 20% background. And once we are done with that, we can go to the Hex analysis. Here you see this little white area that's 6 to WW on a WW background and a top background with varying composition. But here you have a very sensitive, very interesting process sitting on top of swimming in a pool of TT bar and WZ, and that could wiggle. So one need to be very careful with correlations and assumptions, because if you want to be optimal, if you want to be global, things are involved. And finally, we can do like this little signal here on top of an enormous background, where the background is a factor 10 higher. Of course, the analysis can go in parallel. It's just the constraints are triangular. If we want to get the constraints, of course, we have to be very careful to publish complete analysis results with all the correlations. And that's a discussion we're having now in the community. And that is where important decisions are made, and life is difficult. Theorists want everything. Experimentalists only want to provide a number. There must be some middle ground and different strategies coming together, which I cannot explain. That would be a seminar on its own, but that, I believe, is the challenge. Now, finally, let me review the state of the art of SMEFT machine learning. It was, I believe it's fair to say, kicked off with the MedMiner approach, many papers that I link here, which establish much of the ideas and technology towards the statistical interpretation I'm going to discuss on the next slides. I will focus on parametrized classifiers for learning, standard model effective theories, both with neural nets and with tree algorithms. So these are the two things that I will focus on. Now, how do we parameterize? We know from quantum field theory that the differential cross-section is the matrix element squared, and that we get diagrams from standard model effective theory. If you square this amplitude, you get a quadratic polynomial. So we know that our differential cross-section is a quadratic polynomial in the EFT coefficients. Now we inject this into the log likelihood ratio test statistic. The way to do it is, again, to separate off the normalization, so the total number, from the shape. In doing so, it's one need to inject here the Poissonian distribution. One finds that the log likelihood ratio actually can be computed as a sum of the logarithm of the differential cross-section ratio. And that was the polynomial. So all you have to know are universal coefficient functions. I call them here RA, RAB, you can call them N. And these are the things that control the optimal test statistic in all the SMEF parameter space. Note that the curse of dimensionality is lifted. In contrast to supersymmetry, in contrast to many other models, we can, if we have like 15 operators, we can get away with 136 coefficient functions. That seems like a lot, but it's a 15-dimensional space. If that structure was not there, it would mean the series would go on forever, and you would just you would just die like you die in supersymmetry. You cannot get the 15-dimensional SUSY limit from one analysis. You have to do drastic simplifications. The other thing that's important, it's case dependent whether it's important, but it is a fact. The cross-section ratio is not only a polynomial, it's also positive. So you can inject that and write in one way or the other, most general positive polynomial. And now I wrote here estimators n, and those can be neural networks. So now let's parameterize things. Again, let's start with the standard mean squared error loss function, which is in black, which will give you which is the likelihood trick. So here is your f hat, and that will be 1/1 plus r. And the idea is now, do not regress in f hat, regress in 1 plus 1/1 in 1/1 plus r hat, and do also not regress into r hat, but here inject the polynomial structure, and now you put your neural networks here. That's what we call parametrized classifiers. The thetas are something are the variables used for the parametrization, and the neural network, or whatever they are, these estimators are the estimators of the universal cross-section dependence. So you get a neural network, a set of neural networks that predicts these coefficients, and then you get to choose posteriori. That's the point. You get to choose what theta values you want. And from these, you can compute R, and then you're done. This was, I'll show you how this looks like. It's a paper from Andrea Giuliano and collaborators. It was studied in the context of PP to WC. I put here the Atlas measurement. That final state is fairly pure. So we are in the middle ground here of the SMEFT channel. There are two operators. These are the most important ones, and actually they enter in complicated triple correlations of decay angles. Well, then one can assess the optimality of, because you've learned the optimal test statistic in toy data. In toy data, you can control everything. You can control, you can obtain the best toy limit, the theoretical optimum under some assumptions that you make. And you can correct me if I misread it, but I believe the theory optimum is the red contour, and the toy data is extremely close, is the yellow. And then you repeat this from the toy data. You do the same in more complex MATLAB simulation at the leading order and at the next leading order, and the yellow bars here stay approximately the same. So that's a type of validation at the generator level that you can really do this. I implemented this in PyTorch just to have some animation to show. This is a slightly different model, is CH, but uses a similar number of observables. These are two neural nets. I only learn a single coefficient here. I have this plot here because discussing this with my student, they always get confused on what's actually predicted. Predicted is the cross-section ratio. I took here a PT of 500, just taking out the spin. The prediction is 1 plus whatever is blue times theta that you get to choose, plus red times theta squared of your choice. So you learn here the linear term and the quadratic term of the cross-section ratio. It doesn't fit perfectly up here. There are reasons that there are solutions for this. That's the mistake. That's the problem of my implementation. Maybe they can be tuned. But here is a neural network that fits. Observe maybe in the beginning of the loss functions, it wiggles around and then it settles down. This is a proof of principle implementation on a toy. Nothing more.
So
but
this
it's
is
good.
This is a one-dimensional marginal, right? So on what you are training, on how many, so you're training in how many dimensions?
This is just one-dimensional.
Okay, so it's very good.
I tried 2 and 3. We can discuss it later. It didn't work so well, but this is a different discussion. there are still things to improve here. So what happened is actually, and I need to finish in 10 minutes, is actually quite a bit of a miracle, because you start at the pattern level. You get your theory prediction at the pattern level, but now from these patterns you shower. So for the pattern level you shower. You have showered particles. That's many more, thousands maybe. The shower particles hadronize, decay, they reach the detector. They get reconstructed with some ad hoc prescriptions in the detector, and then actually you have to integrate over all these many latent observables that you have very little control over, and then you arrive at the detector level cross-section ratio, and that is what you need for the Newman-Pearson lemma. There is no pattern level here in the Newman-Pearson lemma log likelihood, which is a detector level. So from here you get the superpowers, but how you get from right to left without having to perform this integration. And that's what I borrowed from the MedMiner slides, because it very nicely explains, I believe, the role of the joint distributions, which are much simpler. The joint distribution are the distribution on X and C space simultaneously. So each event characterized at detector level with X has its history with it, which is characterized by the pattern level and all the other latent observables. In the joint space, one can take the likelihood ratio, divide it, because it is, I mean, it's to be divided, factor out the interactable complicated factors, and they cancel. So the likelihood ratio in the joint space has a much simpler structure that we much better control that we have much better control over from the pattern level. That's the first ingredient. The second ingredient is, when we derive a classifier, we always regress, that the regressor can only depend on the observables, while now in the simulation, everything depends, each event will give you an observed set of features, but it will carry its history with it. So what we usually do is we write a loss function with, here we have some function fxc, and here is a regressor that does not depend on the C. If you minimize this loss function, you will find that it gives you a ratio of integrals, and that ratio of integrals are over the histories. So one sort of digests this, because I have not told you what the F could be, but now let's take this solution and let's use as a function F the joint likelihood ratio depending on X and C that we've defined above. If you insert here, you will find that the hypothesis you simulated at cancels, and you get the proper ratio of integrals, and that is what the term on the right hand side is what you actually want. It's the likelihood ratio at the detector level with the latent space correctly integrated, obtained from a loss function that you really get from the simulation, okay, which is a much bigger but simpler space, and you arrive at something in a smaller space, namely at the detector level. And that's the thing that you need, because that's what enters the Newman-Pearson lemma. I've only said the trivialities, but these trivialities account for a bit of a miracle that we can do this, and all the parametrized classifiers use this. So in the last 5 minutes, I will take this 5 minutes. I will go to boosting algorithms, because they exploit this structure to the maximum. We have event simulation here at the pattern level. We can think of events arranged in bins or not in bins. That's not important. We can re-evaluate this simulated matrix element at a set of parameter points, and we arrive at a SMEF dependent weight that characterizes how the individual simulated event contributes to this region in phase space. And these weights are related to the joint likelihood ratio, depending on X and C. These weights is just they are polynomial by the same reason why everything in all the SMEF predictions are polynomial. They allow us to obtain predictions for all X and C and theta. So we can use these weight functions to, minor people call this morphing, to move in parameter space and get morphed, if you want, I would say reweighted distributions. Now let's try to learn the cross-section ratio with a tree algorithm. A tree algorithm is something that assigns a prediction to a box, and that box is a subregion in a partitioning of your high-dimensional phase space. So it's in principle, it's a complete triviality. It's a very simple thing. Mathematically, it is written as an index function. That thing accounts for the boxing. There is a region J. You put in the event X. This is 1 if X belongs to the region J, and this Fj here, that's your predictive function. Now, if you take your tree, it may be axis aligned, so you put your you define your boxes within on the input variables, and you train that tree to the data, which means at each point you iteratively progress through the tree depth, and you go through all the cut possibilities that you have, and minimize some loss function from that. You will get a very bad prediction because it is boxes by definition. The way to improve the tree prediction is by a method called boosting, which I will discuss after we've gone. I really need to stop now. After, and these two things I probably want to say after we've gone through a very simple example. Let us learn a local version of the model. It's a likelihood ratio constrained to small parameters. This is what we call the score vector. Formally, one can write a loss function for the score vector on the joint space, and we measure the individual components of the score vector with a tree algorithm. The formal solution works as before, but now what we can do is we can take that loss function on the joint space and we can interpret it in the simulation, and each piece has its meaning. The standard model value would just be the weight evaluated at 0. The score vector goes into a ratio of the weight coefficients of this parameterization, and then one can evaluate the tree ansatz. What's computationally important here is that because this algorithm just boxes the events, you get a predictive function that's a ratio of sums of coefficients of these weights. This means that there is in the predictor there's no tunable parameter. And that's in contrast to a neural network. A neural network will always has a degree of freedom that predicts the quantity it's supposed to regress in. In this case, we can analytically solve for the prediction inside the box, and that accounts for at least a factor of 10 in speed up. If you interpret this maybe complicated loss function in terms of things that you know, you find that the algorithm tries to maximize the Fisher information in the parameter measurement. And that's intuitively clear because we have the score vector here. We want to estimate the score vector. So our predictor wants to minimize the variance of the score. But the variance of the score is precisely the statistical definition of the Fisher information, which gives you the lower bound on the uncertainty in the regression. So maybe I should stop here. What I do want to show is that this is a 3-parameter 500,000 event. Is the same thing as with the neural nets. That's a CH model, and here we learn that's 3 parameters. So we have 9 coefficients in 15 variables, and that was in 9 minutes. 9 minutes of training time is also a toy. Okay, is not realistic. We have many features here. You see a very you see an approximation that's like gradient descent. You gradually approach things that's by that's very characteristic of how trees fit. You see that it first learns the most important features, which are energy dependent, and then later on it learns the angular features of the decay plane that I've explained in the neural network context. Now, in the same sense as before, we assess optimality. The optimal contour is the theory optimum is the red one. With the algorithm we get in the toy study, we can approximate it very accurately, and we also used this to check focus on this middle plot here to show the improvement compared to a traditional strategy. So that's the last thing I'm going to say. The traditional strategy was the ones that I discussed first. Actually, that's used in the Run 2 paper of this analysis, which is a C boson plus a Higgs boson. You train a deep neural network to remove the background. You see there's enormous background. There's just a little bit of signal. And then with what is left, you try to get a good test statistic, can be some momentum, and then you do your interpretation. This will give you this shaded contour. If you learn the whole cross-section ratio, including the backgrounds at once, you get limits that are significantly tighter. Good. I spare you my general thoughts on the SMEF channel, on the SMEF challenge. This we've already discussed. I stop. Thank you.